Okay. See, yesterday we brought some important concept. I want to recap those concepts because some of those things first time when you hear it will be difficult for you to understand. So we will recap some of those concepts. Then we will move. Okay. So I'm telling this is Earth. Okay, below this you assume this is the earth line. Okay, now our friend Alan Joshen is standing on top of it. Okay, what is mass of Alan, what is your mass?
40.
40 kg. So Alan Joshen, who is 40 kg in mass, is standing on earth, right? What is the force of attraction between Alan and Earth? What is the force of attraction between Alan and Earth?
Gravity.
Gravity.
Okay, how much is that force?
9.8.
9.8 into 40.
10 raised to minus.
I hear all those. I slightly modified the Earth, made it round. Okay, so now I made Alan standing. Okay, so you told it is gravity. It is gravitational attraction. Okay, so what are the points which we told? What are the important things to consider about this gravitational attraction? It is starting from where to where? The gravitational attraction starts from where to where, or between which points?
The center of mass and center of gravity.
Yeah, from center of Earth to center of mass of Alan, right? So this concept you understand. Center of Earth to center of mass of Alan. Yes. Okay. Right? This much clear? Right. And then it is a force of attraction. Right? Alan is loving Earth. Earth is loving Alan. But he can't go down because there is soil. Otherwise, he would have gone down. Depth. But certain kind of soil will love you too much. Sand and water and all will love you too much. Okay. So you will go down. Right? So because of this, you will go down. But in the soils which we stand, uh, the sand actually provides bit more strength so that he doesn't go down or you don't go down. You understand that, right? Now, how do you calculate this force? How much is that? What is the force? You told it is gravitational force. Let me call it as F gravitational force. What is that gravitational force? How do we calculate between Alan and Earth?
9.8 into 40.
Yeah, 9.8 into 40. So where from you got this 9.8? So that's what I'm telling. Let me ask students who have come. Do you understand this concept that if something is proportional to something, then let us assume uh, uh, a force is proportional to say something. Then we write force is equal to a constant into that something. Have you learned this? How this is done? This is done in physics, maths. Do you understand this?
Yes, sir.
Younger students, 7th, 8th students, do you understand this?
Sir.
Yes or no? Yeah, somebody tell yes or no.
Yes,
Tell
sir.
it. Okay.
I don't know about it.
Okay, fine. So it is like this. So you have to understand that concept. Let us assume you are traveling at some speed, right? And you cover some distance. So Ayati is traveling from her house in Mumbai, Airoli, and she is now cycling. Let us assume she is cycling to Colaba, right? So the distance she has covered from her house is directly proportional to her speed. Can I tell like that? Ayati is starting from Airoli, her house, and she is cycling towards Colaba. Now, the distance she has covered is directly proportional to her speed. Can you tell like that? Is that a right statement to make?
Yes.
Yes. Why it is right statement?
Distance increases while
Speed increase. Yes. So that is the meaning of proportional, directly proportional. Directly proportional means when this increases, that will increase. So when speed increases, the distance covered will increase. But then there is a catch there. When speed decreases, distance covered doesn't decrease. The increment in distance covered or distance covered in a specific time will reduce. But let us simplicity sake, let us take it like distance traveled is proportional to speed. So if IRT is cycling at 10 km per hour, then she will cover, let us assume in 1 hour 10 km, in 2 hours 20 km. Okay. Assume Prajakta has made biryani in the afternoon and she is riding at 20 km per hour. So in 2 hours she will cover 40 km. Is it not? So that is what we tell proportional, directly proportional. So then how do we get the distance? Distance is, so we tell in such kind of things, we tell distance, assume distance is directly proportional. I am using this symbol, okay, for that. Assume this is directly proportional. It's directly proportional to speed. Right? Distance covered by IRT is directly proportional to speed. Now, then I can write this as distance is equal to a constant into speed. Because proportional means what? When speed increases, distance increases. So the question is, how much the distance will increase when speed increases? That is that constant. So once you are telling when speed increases, distance will increase. How much it will increase? Let us assume speed increases from 1 to 5. How much will distance increase? That is that constant. Now you tell me in the case of distance and speed, what is that constant? If distance is equal to constant into speed, what is that constant?
Time.
That is time, right? In the case of this thing, it is, this constant is time. Do you get that? But for different cases, it will be different. So you see where from it is coming. This time is like if you multiply speed with time, you get distance. So speed, if it is 10 km per hour in 2 hours, 2 into 10. If it is 20 km per hour in 2 hours, 2 into 20. It is, let us assume 5 hours, 5 into 20. So in this case, the proportionality, when you convert into equation equal to that constant is speed. Right? Can you think about one more relationship directly proportional? We talked about distance and speed. Can you think about some other parameter where directly proportional to something else? Where you can tell this is directly proportional to this.
Sir, in cooking.
Cooking. Yeah. Tell me what.
I don't know the exact proportion, but if you take 2 glass of dal and rice, I don't know exactly what it is, but
Yeah. So how much final rice you will get, right?
yes, sir.
Yeah. That is good, right? For example, you cook something. So how much you put as input quantity and output quantity, it is directly proportional. That is right. No doubt. But it is both quantity. It is slightly simpler example. I can tell an inversely proportional in cooking. Ayati. Inversely proportional is opposite to this. When this increases, this will reduce. In cooking, I can straight away tell something which is inversely proportional. Ayati, or the cookers here, pastry chef, Meka.
Yes, sir.
Yeah, can you tell? Can you think?
Sir, inversely proportional in cooking.
In cooking, there is something, some phenomenon which is inversely proportional. Inversely means if this
Boiling?
is, yeah, the time taken for something to cook is inversely proportional to the temperature which you give, right? The more you heat it, less time it will take. Is it not? Is it not? The more you heat something, the less time it will take to cook. So that is inversely proportional. If the heat is more, the time taken is reduced. So these are relationship. Can you think about something else directly proportional? There are diamond does it. Just think. Just think. Any other examples?
For what?
What, Avijit?
Wattage.
Wattage. Proportional to what?
Current.
Yes. He is right. He's very much right. It's a brilliant example. As the world of electricity is going running. So the more the current, the power is more. If the more current is there, the power is more. Okay, and there the proportionality constant is something else. So there are so many examples like that. You can tell number of electrons and current. The more the number of electrons, you have more current. Is it not? Do you agree? Do you agree or not? Is it not? The more electrons are traveling, you have more current. Correct? Brightness of sunlight decreases as the distance from sun is increased. Yeah, see, inversely proportional examples she has given. So these are the simple examples. Now let us come back. What did we tell in the case of gravitational force? Let me call gravitational force as Fg. Okay, assume it is gravitational force between Alan. We have kept Alan on the top of Earth so much time when we are discussing about proportionality. Okay, he's standing still there. Let us close this business. So the gravitational attraction between him and Earth is, we are telling it is proportional to two things. Which all are the two things? The gravitational attraction between Alan and Earth is proportional to which all things? See, if you can tell, it is easier for me, because when I am writing, I have to go to chat, open it, and read it. If you tell, it is easy. Otherwise, mass of what?
Mass of Earth and Alan.
Mass of Earth and Alan. Do you all agree to this? Do you all agree?
Yes.
Others agree with Rishikesh?
Yes, sir.
Yeah, it is not the mass of Alfin and Earth. It is not the mass of Alan's family and Earth. See, when it comes to the business between gravity between Alan and Earth, he is alone in this world. Okay, none of his friends, his brother, family comes to help. It is purely him, right? Okay, so it is mass of Alan. How much was that? 40. And mass of Earth, let me call it as m. What else it is proportional to?
Distance between mass of Earth and center of mass of Earth and center of mass of Alan.
Okay, and is that directly proportional?
Inversely proportional.
That is inversely proportional. You see, that is what you have to remember. So the mass, if it is more, if Alan's mass is more, he will attract Earth more, Earth will attract him more. But the distance between Alan and Earth, for example, instead of standing on here, if he is standing on top of Burj Khalifa, the attraction will be more or less.
Less.
Less. Because he is standing on top of Burj Khalifa, so his distance from the center of the Earth is increased. Okay? Or if he is 100 kilometers above, that is why after some point there is no gravity. Right? The reason why there is no gravity after some point is because of this thing. When the distance is increased, gravity reduces. So this is inversely proportional to not just the distance, and it is the square of the distance. So what is the distance? that distance is, let me take something here. So that distance is from the center of Earth till, let us assume this is the center of planet. It is still here. Do you understand?
Yes, sir.
Yeah. So now assume our friend Alan is not here. Alan is not here. Alan, so somebody has taken him and he is here. So then this distance increases till here. You understand? So it is always the distance between center of the Earth and
Yes.
Allen center, wherever he is. But this kind of situations are less, and normally Earth's radius is how much approximately radius of Earth? Very rough. Very rough value of Earth radius.
6.4 to 10
Yeah, around 6,400 kilometer, right? Around 6,400 kilometer is the radius of that. What is the distance between Mumbai to Kerala? Ayati, where she is sitting, and Kerala, what is the distance? Yeah, you also have Google, right? Just browse.
Around, because from here to Konkan it is 350 somewhat.
Okay. Just browse and see what is the distance between Mumbai and, let's say, Palakkad or Thrissur or Ernakulam, between Mecca and Ayati.
1,220 kilometers.
How much? How much?
1,220.
Yeah, around 1,200, right? So this is almost 5 times. This is almost, yeah, almost 5 times, approximately 4 to 5 times. Radius of Earth is almost 4 to 5 times of distance between Thrissur and Mumbai, or Trivandrum and Mumbai. So you should have that idea. When you tell Earth radius, how much is that? You should have some idea, rough idea. Okay, right? Okay. So now you see now, normally, let us assume in the tallest of the building on the Earth will be some, or the tallest of the place where you can go is a 1 kilometer, 2 kilometer, 5 kilometer, 10 kilometer. So compared to the 6,400 kilometer, that distance doesn't make much difference. So for all practical purposes, when we calculate the gravitational attraction between an object and Earth, we take the value of Earth radius. You know why we take Earth radius? That is because Earth radius is around 6,400, but you can't take Earth radius if the person is not on Earth's surface much above. You have to take Earth radius plus this height you take. But normally when you tell, okay, what is your mass, what is your weight, what is the force, you are talking about things which are happening above Earth or 1 or 2 kilometer above Earth. So you take the value as the radius of Earth. Okay, so if I take it as R, this is square of R. You understand? Now this is proportional. How do I make this equal to? What should be done?
By introducing a constant.
Yeah, like we learned previously, if something is proportional to something else, means when this increases, this value increases, this will increase. So if you have to convert it into equality, you have to multiply with one constant. In our distance case, it was time. In the watt case, it was something else. So here, that constant is what we call as gravitational constant. And our friend called Newton bro has calculated the value of this, which is universal. So rest of the part is same. Rest of this part is same. But this is G into 40 amperes. You understand? So now this is what we call as gravitational equation. Now in this case, you see this G is constant. Mass of Earth is constant. R, radius of Earth is constant. So for all activities which are happening on Earth's surface, we can take this as, we take this 40 is the only thing varies, because if it is Alan, it is 40. If it is Ayadi, it is something else. If it is between a mountain and earth, it is some other way. If it is between a car and earth, it is something else. So all the things are constant. So this G, this M by R square, this value is a constant because all the parameters in that is constant, which is what you calculated yesterday. Avinash, how much you got the value?
Sir, can you repeat?
No,
Network.
what is the value you got? GM by R square, you got it as 9.8 or 8.2 or something, right? Yeah. So this is what we call as for anything. Here it is Allen, so it is 40. Assume it is not Allen. Assume it is not Allen, some object. What is the gravitational acceleration of some object, say A? Then it is mass of A into 9.8. Mass of A into 9.8. So what is now, you can tell what is the force with which each of you attract Earth? You tell me now, each of you. What is the force with which each of you attract Earth? What is the force with which IRT attracts Earth or Earth attracts IRT? For each of you, just calculate and message. For Alan, we already calculated 40 into 9.8, approximately 400, slightly lower than that. So 400 Newton is the force with which Alan is attracting Earth, and Earth is attracting Alan. Right? Okay. For others, what is the force with which you attract Earth? $588 for Avinash. Ari, how come it is 6.04 for Rishikesh? It can't be. It is 9.8 into your mass, right? Mega, it is, see, Mega is attracting Earth so feeble. See, Mega, you have to attract Earth with so much higher force so that Earth recognizes you. Right? Yeah, Mega? Okay, so you have to keep some muscle, or you have to keep some weight on your head, something like that, so that you can attract more. Okay. So jokes apart, this is the each of you, yeah, IRT is attracting 411. Okay, so if you are holding something in your hand which is having this mass, that mass will also get added. Right? Understand? That is why let us assume you are fallen into water. If you have a stone on your back, chances of you sinking are more because attraction is more. Ripriya, it is 313. Mass of Earth, yeah, see, yeah, here we all use in this thing in meter, second, SI units. Okay, so all of you are calculating. Okay, fine. So you understood? So any object, the force of attraction, if the object is in Earth's surface, okay, the force of attraction between that object and Earth is 9.8 into its mass. So this is what we call as weight. Right? Okay, weight. Right. So I am just scrubbing this. So if you want to note this, this is not there in my presentation. If you want to note this, you can note this. So if you take screenshot, you can take screenshot. So I'm going to rub this. Okay. Already it's over. This is very important concept. Okay. We are going to come back to this concept later to tell what is this 9.8. What is its business? That man is very important. That 9.8 man is very important. Okay, we'll come back to that. He's very important in the solar system, right? Okay. So now what we understood, this M is Earth mass. So if you go to another planet, you use that planet's mass, and the R that planet's radius. Okay. There are some more complications here which I am not getting into. Which we'll see here. So shall I rub? Okay. Yes. So now I'm giving you an assignment, slightly tricky problem. Okay, let your kidney work. Okay, so I'm giving three cases, three places. This is for you, homework. Go and do at home assignment. So let us assume you are lifting a person, like yesterday we saw Shadowcan lifting. You are lifting a person. Where will the weight be more? Whether it is on Earth's surface, which is like here, case number 1, or Everest, you are lifting the same person on top of Everest, which is 9 km above Earth's surface, or KGF, Kolar field, which is 3 km below the Earth's surface. Where will the weight be more? Weight means the force between. The weight is the force. So when you lift somebody, what are you doing? So when you lift somebody, see, I want to lift Alan Josh. Alan's girlfriend wants to lift Alan. What force she has to overcome?
Gravitational force.
Yeah, what? How much is the value?
40 into 9.8.
40 into 9.8. See? So lifting Mega is much more easier than lifting Alan. See, lifting Avinash is much more difficult. Right? So as youngsters, I am giving you a very good clue. Okay. Right? So lifting everyone is not same. Right? Okay, cinema and film, you will see all those things, your back will break. Look. Okay, so there are many ways of expressing love. Lifting is one method. Be careful. Science applies there. Right? So now, if you have to lift Alan, 400 Newton you have to apply to lift. Right? If it is somebody else, that Avinash guy, if you have to lift, your back will break. You have to eat mutton biryani. Understand? So now,
I am 6'8",
yeah. So now, if you lift in these three scenarios, where will the weight be more? Means where it will be difficult to lift or easier to lift. Weight more means weight is this 40 into 9.8, what we calculate, mass into 9.8. Okay, take the screenshot. This is your assignment for the day. Can we move on? That is a bit tricky, okay? That is a bit tricky. Don't think it is straightforward and simple. Okay, apply your technique. Okay, smoke has to come from the head. Okay, spend some time.
Sir, do we have to explain or?
Yeah. See, I just give you problem. How you address problem, how you give answer. It's all up to you. This is not school test. Okay, you can write answer as a poem, you can paint the answer, you can give a video, you can give an audio, all these provisions are there. So all left to your creativity. See, look how Navjit has put his name in Zoom. All left to your creativity. Right? Yeah. So there are people who do attack with art here, you know. So all left to your creativity. Okay, right? See, okay, now we come to this person, dangerous person, who changed science for good. We told one of his area that he improvised the telescope and he actually propagated that Copernicus concept, and he was the person who put the final nail in the coffin of geocentric universe. He didn't stop there. He was continuing to do experiments when he was under house arrest. Right? So I don't know whether you heard about the story that Galileo went to Pisa's tower and he put balls of different weight and he observed which is falling first. Have you heard about such a story? Yeah. What is the story? Tell me, one of you. What is the story? Somebody who has heard the story, tell what is the story?
Sir, can you repeat it again?
No, there is a story, famous story, myth that Galileo went to Pisa's landing tower and from the top he dropped multiple objects to see which one falls first. Yeah, Pisa tower, not this Pisa, or the other Pisa. Okay, two weights. Yeah, correct. Okay, yes, right. So that is a story which most probably is a myth, untrue. Okay, but he did that experiment through different methods. Okay, attempt this. Attempt this ball. If you have a doubt, ask. If you don't understand the question, all of you attempt this ball. So you're dropping two iron balls from the same height. One is 1 kg, second is 2 kg. Which will drop first? Which will fall? Which will hit the ground first? Everyone?
Sorry, is it in free fall?
Yeah, you think it is free fall. That's why I put it is same material ball. There is no trick here. Okay, it's a very straightforward. I assume all other conditions are same. It's ball, metal ball, so you can assume friction is same for both. Remaining 14 people only have answered. Quickly, last 15 seconds. Everyone attempt. Okay. Shall I close? So only 15 of you attempted. I am closing the call. So the answer is predicable lines. This is how you answered. That's what you normally, the common sense will tell, that the 2 kg will fall first. And 4 people got the right answer, that both falls together. That's okay, no problem. So this is another misconception which most of the people, students have. Now, that is what this gentleman bust. That myth is what this gentleman bust. So during the old Aristotelian theory was that the heavier one will fall first. So those 4 people who told the both will fall together, one of you please explain why. I told you yours is right answer.
Yes, I can. Because the Earth attracts everything in an equal force. We learned that the acceleration is 9.8 meter per second. All the object attract Earth. All the object attract Earth attract all the objects at same force, same acceleration. So all.
Why it is same? Just now we studied that the force of attraction between Avinash and Earth is higher than force of attraction
Same
between
acceleration, sir.
Why same acceleration is the question. See, we just know what we studied. If an object's mass is more, the force of attraction is more. That is why Mega's attraction is lesser than Avinash. Is it not? So the gravitational attraction is more for 2 kg. That is the common sense. That is why normally everybody thinks the gravitational attraction of 2 kg. What will be the gravitational attraction between 2 kg and Earth? What is the gravitational attraction between the 2 kg ball and the Earth?
18.6.
9.8 into 2 kg, right? All of you understand? It is 2 kg into 9.8. What is the gravitational attraction between 1 kg and Earth?
9.8.
1 into 9.8. So obviously 2 kg ball is being attracted by Earth with a higher force. But both falls at the same time. Why? Think about it. The coming classes will address the answer, but think about it. Now, these are the core of Newtonian physics. Okay, these are points at the core. Okay, so think about it. Now, coming to this, you know what he did? The Pisa stuff would have been easier. Why they would have selected Pisa's tower? Because it's a leaning tower, so it is easy to draw. what he actually did is he made such slanting surfaces with a sort of zero friction groove, and he made balls of different weight, different mass, sorry, different mass, and he started dropping them one by one. Drop one ball and see how much time it takes to reach here. Drop from here, see how much time it takes to reach here. Another ball. So different mass balls, he tried to drop from here and measure the time which is taken. So, to his surprise, he saw that all are reaching at the same time. Whether it is 1 kg, 2 kg, 5 kg, all the balls when you put from here, it reaches at the same time. Actually, the method which he deployed was he kept a water bowl here, because that time this kind of accurate time clocks were not there. He kept a water bowl here and calculated the water which is getting spilled out, which is a measure of the speed which you attain. So he identified, he understood that the time taken by the balls is same and the speed of all the balls when you are here is same. He realized it. So that is the starting point of today's physics. So he then, that is against the Aristotelian concept. The concept was that, the gravity concept was that if the heavier the ball is, it should take more time. It should take less time, because the force of attraction is more. He understands gravity and all. Galileo and all, they understand gravity and all pretty well. So that is from where he comes up with this concept of inertia. That is the point from where he gets the concept of inertia. Just focus here. Just focus here. See, he did one more experiment and understood that he tried to change the length of this experimental setup. The length of experimental setup. And then he started measuring, is there a relationship between the time taken for the ball to reach the down point and the length of this? You see, he started up, is there a relationship? And he conducted this experiment so many times and he realized there is a relationship between both. Between the distance traveled or the length of this groove, whatever this, he drops here and collects here, which is the length of the groove, which is the distance traveled, let us assume which is d. So he realized that it is directly proportional to square of the time. Square of the time taken. So that was his observation. So for example, if this distance is say 10-meter length, so it is the time taken, it is proportional to the square of the time. For example, if this one is taking 5 seconds, when you are increasing the distance, obviously it will take more time, but the proportionality is not direct. It is not distance is proportional to time. This distance is proportional to time square. Now comes the brilliance. Now comes the brilliance. The brilliance is time square is time into time, right? Time square is time into time. So you can bring, then he wants to see if distance is proportional to time square, then what is proportional to time? Time square is proportional to distance. What is proportional to time? He wants to get time is proportional to what? So what he did, he took one time to the other side. Time square, as all of you know, is time into time, right? T into t, right? Time square means time into time. Now he wants to see what is the proportional stuff for time. So he took one time to the other side. So what will come? So it will come as distance by time, because when something goes from one side of the equation to the other side, multiplication will become division, plus will become minus. That is the basic stuffs of math. So then he got time is proportional to distance by time. What is distance by time?
Speed.
That is speed. So he realized that speed is proportional to time, which means when the time increases, when you drop a ball from the top, when the time passes, speed is increasing. When time is increasing, speed is increasing. So what do you call that? Increase in speed. What do you call that?
Acceleration.
That is what you call as acceleration or deceleration, increase or decrease. So this is a big moment. So in the earlier times, the Aristotelian times, they believed that a force is needed to move something, which means to produce speed is what you apply force. But here, there is a force, he realized, that is the gravitational force. That is the gravitational force. See, this is falling from top to down because of gravitational force, that he understood. So now, the gravitational force, when it is continuously applied over a time, it is not producing a constant speed, it is producing acceleration. That is the big moment. And it changes the entire science we will see in the next class. So the concept changes that you need a force to move something, so Earth cannot move because you don't have a force. From there, it changes to this concept that when you apply a force, it changes the speed. That means if you don't apply a force, if something is moving in a speed, if you don't apply a force, speed will not change. That is what we call as inertia. So if something is moving in some speed, if you don't apply a force, its speed will not change. If you apply a force over time, speed will change. That is the concept of inertia, which is actually the contribution of Galileo. The first law of Newton, what we call, is actually the contribution of Galileo. And this is the root from where it comes. Do you get that? You have to spend some time on this, okay? Go home and spend some time. This is the crux of what we call as Newtonian physics. Okay, we'll spend much more advanced things in the coming class, but spend some time on this. Okay? So we stop at this point today. If you want to write this or take screenshot, you do that. Tomorrow we will continue, and then we will get into a bit more things of Galileo. And for today, we stop it at this point. Any doubts? Any doubts?